دكتور بصراحة أنا كان عندي سؤال بخصوص سؤال الكويز
which is
اللي
which
هو
one؟
تبع السي او بي. هلا هو مكتوب بالحل المفروض يعني 5 مرات أحطه رايت.
هي بتطلع 4 وشوي.
هلا أنا فرضتها 4. أوكي بس ليش دكتور ليش يعني ليش 5؟
هي بتطلع 4 وشحطة. ماشي.
أوكي
فإذا أنت يعني بدك تاخذ السيلينج لعدد المرات.
أوكي بس هلا مثلا هو السي او بي الواحد التايم اوت تبعه مش 0.9 something.
بالضبط.
اوكي انا فرضته مثلا اتس 1 ملي سكند. هلا وانا عندي البروجرام تبعي 4 ملي سكند، فمش لازم احط يعني 3 مرات انه ان بتوين.
لا ليش 4؟
يعني مثلا بعد الثانيه الاولى
بدك مرة تسوي كلير، بعد
هاي مره.
الثالثة الثانية، وبعد الثالثة وبعد الرابعة.
ليه بعد الرابعه؟ مش هو اصلا 4 ملي سكند مش المفروض خلاص؟
لا ما
يعني ليه
هو
بحط؟
على لوب، هذا برنامج فيش امبيدد سيستم بيسوي اللوب مرة واحدة وبيخلص. يعني حكيناها أكثر من مرة يا زلمة إنه الامبيدد سيستمز عادة في بيسوي نفس التاسك اوفر اند اوفر. فذا مين
اوكي
لوب لما احكي لك the main loop in the program معناها this loop is repeated over and over. مزبوط؟
اوكي يس.
عرفت كيف؟ this is the idea.
اوكي تمام 100%.
تمام؟ اوكي. طيب other questions؟
يعطيك العافيه دكتور.
اهلا باسل.
دكتور انا مش راح اقدر احضر اليوم، بس بدي اسال اذا ممكن يعني متى ترفع المحاضره على اليوتيوب؟
انا مباشره برفعها اول ما تخلص الليكتشر، بسوي لها اكسبورت وبرفعها، يعني 10 minutes بتكون اونلاين دائما.
اوكي تمام.
اوكي ماشي.
ماشي شكرا. عفوا لازم اطلع دكتور.
لا مش مشكله.
شكرا.
تمام. alright. خلينا معناته to move to our lecture. Basically today we are going to start a new chapter which is chapter 8. And chapter 8 basically covers an important aspect that is usually and frequently used in embedded systems, which is performing or carrying out operations that are related to time. And hence this chapter is about the timer module or the timer system that is available in the HCS12 microcontrollers. And this is, as I said, is very frequent. It is very common in embedded systems that you need to work with or to perform operations that are related to time. That's why if you look at most microcontrollers, even the basic ones, the basic models, they are usually they usually have a timer system or a hardware that can perform time operations related to time. So basically we'll cover in this chapter, we will go very quickly about the idea of timing, the need of timing operations in embedded systems and the type of operations that are usually encountered. Then we will go into details and discuss the timer function or the timer system that is available in the HCS12 microcontrollers. Basically, this timer system is huge. Actually, it provides a lot of operations, a lot of functions. So in this, I divided the chapter into 2 parts. In the first part, I will cover the 3 timing operations: free running counter, input capture functions, and output compare functions. And in the second part, we'll cover other timing functions that are related to this timer system module, and another timing module which is the pulse width modulation module. So basically, as I said, in embedded systems, you usually need to implement or to use some or to perform some operations that are related to time, that need time in order to perform these operations. For example, you might need to measure the time between 2 events. So you need a time base or a time reference and a way to monitor these two events in order to measure the time between these two events. For example, when the first event occurs, you record the time, and then when the second event occurs, you record the time of that event. So the time between the two events can be calculated as the difference between the two events. Also, for example, you might need to generate time delay, and we already discussed this when we talked in chapter 4, when we where we said we can generate time delay using by writing a set of instructions, certain sequence of instructions, in order to waste the microcontroller time. And we said we can put this code in a subroutine. However, this is called software generated delay, which basically, in order to have or to generate this delay, you need to execute these instructions. So this implies that your CPU will be always busy while generating this delay. What if you want to perform other operations while you are waiting for this delay, while you are measuring this time, you are generating this time? You cannot do this easily in the software-based approach to for generating time delays. What is the solution? The solution basically is to free the CPU from generating the time delay and use another resource that can generate time, that can measure time. And this is one of the functions that are usually associated with the timer systems or the timer modules that are found inside microcontrollers, which is basically to measure, to generate time that can be used as a time delay without involving the CPU. The CPU is minimally involved by configuring this timer system in order to measure some period of time. Another thing that might force you to go to the timer system or to the hardware basically to generate the time is the accuracy of the generated time. For example, consider the case when you are generating time delay using software. So you are basically, your CPU is basically generating, executing instructions to waste the time. So in addition to the disadvantage of occupying or using the resources of the CPU to generate the time delay, this time delay might not be accurate. For example, consider the case when you are using interrupts and the interrupts are enabled and some interrupt happens or occurs while you are generating, while the CPU is generating the time delay using software. So what will happen? The CPU will stop the generation of the time delay, will go and service the interrupt, then it will come back and continue the generation of the time. So effectively, the time that is generated using the subroutine or the delay subroutine is not the time that it was designed for, because now it becomes the delay subroutine time plus the time that was consumed in servicing the interrupt. That's why if your time delay is sensitive, is used in some sensitive application where you cannot tolerate the change in the delay value, and you are in need to enable the interrupts, then the software-based approach for generating time delays might not be accurate or might not be useful in this case, because the time delay might increase in case there is an interrupt. So basically, in the timer system, you have some reference time that you can use it to implement different operations. One of them is generating time delay. Other applications might be period and pulse width measurement, to count events, to record the arrival of some event, periodic interrupt generation. For example, as we saw in the real-time interrupt. Real-time interrupt, basically, it is a time. It is a timer. It is a counter that can interrupt the CPU after a certain period of time that is programmable, as we saw earlier. So the timer system can be used also to interrupt the CPU every certain period of time. Every certain period of time, similar to the RTI interrupt. So this module or this timer system provides you with another source of periodic interrupt generation, and so on. So basically, if you have the timer system, you have a clock, and this clock you can use it to measure time, and based on the measured time, you can perform different types of operation. You can record that time. You can record when the time reaches certain value, and based on that, you perform certain event, which we call output capture operation. When some event arrives, you want to record the time, so you have to monitor that event, and once you receive it, you just record the time. So this is called input capture operation. So this will be discussed later. Now, these operations can be somehow implemented in hardware, in software, I'm sorry. However, their implementation is kind of difficult, and at the same time, you are using the CPU to implement these operations completely. So this will consume the resources of the CPU. And here comes the advantage of integrating a timer system inside the microcontroller, where you can delegate the time-related operations to this system and free the CPU to do other types of operations. This is actually the one basic design aspect. Whenever you want to free the CPU from doing certain tasks, you need to dedicate a separate hardware or an additional hardware to do that. And because some of the operations can be done by the CPU, but they will consume the resources of the CPU. So if you want to free the CPU, basically you need to add additional hardware that implement or supports these tasks. So there normally, as I said, there's a dedicated hardware that implement the timing functions, and it can be used as in the same manner we work with other peripheral devices. So this is here a simple figure to show some of the applications of the time. And simply, as I said, the timer system basically is a clock that is continuously running. And this running time, you can use it to perform different types of operation, to record the time of the occurrence of some event, to perform some event when some instant of time, some time is reached, and so on. So all of these operations can be performed if you have a clock. So the central part or the major component in the timing system is basically a timer or the hardware that is capable of generating time. So basically this piece of hardware is a counter or timer. Sometimes we say timer, sometimes we say counter. It depends on how you trigger this hardware. So for example, here we have on the figure an 8-bit counter or timer. An 8-bit counter or timer, which is basically an 8 flip-flops, JK flip-flops. The inputs of the JK flip-flops are connected to logic high, and the clock of the first flip-flop is connected to some external input. The trigger of the first flip-flop is connected to some external trigger, while the clock of the remaining flip-flops are connected to the output of the previous flip-flop like this. So I don't want to go into the details and analyze the behavior of this counter, but basically what we have here, I guess everyone knows what is a JK flip-flop. It is a storage element where here is the stored value, the Q, and these inputs, the J and K, control what happens to the stored value when the flip-flop is excited, when the flip-flop is triggered. And here we have a negative trigger, negative edge triggered flip-flop. In other words, whenever there is a falling edge on this input, which is we call the clock, the flip-flop is allowed, or the inputs J and K are allowed to affect the stored value. So for example, in our case here, both J and K are 1, 1. So whenever there is a falling edge on the input, then the J and K values may affect Q. And since J and K are fixed to 1, 1, 1, 1 on a JK flip-flop implies toggle. Toggle or complement implies that complement the stored value. So if the stored value is 0, then upon the arrival of the falling edge, Q will become 1. And if the stored value is 1, when the falling edge or the negative edge is observed on the input, then the 1 becomes a 0. This operation, we call it toggle, and it happens when both J and K are 1 by the time the edge arrives. Okay, so this flip-flop, the first one to the left, the most left flip-flop, basically it changes the stored value on every falling edge, So let me just show the timing diagram for the first two flip-flops. Let's assume we have two, the first, I don't want to make it, the first two flip-flops. Let's look at the first two flip-flops, which is basically a 2-bit asynchronous counter. So let me share the video. So basically, usually at the input, we have a periodic square wave, which represents the clock or the trigger. So let's assume we have, this is the clock or the input. Like this. So this is the inputs. And then we have a Q0, which is the least significant bit of the counter, and the Q1, which is the most significant bit of the counter. Now, if we assume that Q0 is initially 0 at this moment. So now Q0 is only allowed to change at the falling edge, which is here. So before this time, Q0 will remain 0. Now at this instant of time, there is a falling edge. So both J and K are allowed to affect Q. And the way they affect Q now is toggle. So now Q0 becomes 1, and it will stay 1 until another falling edge is observed. So now it is again toggle. And here it is again toggle. And here it is toggle, like this. So on every falling edge, Q0 is basically complementing its value. Now, how about Q1? If you look at Q1, its J and K inputs are also connected to 1, 1, which means that Q will toggle, but it will not toggle whenever the input changes from 1 to 0. It will toggle whenever its clock, which is here, changes from 1 to 0. And the clock for Q1 is basically Q0. So Q0 is the clock or the trigger. So every falling edge on the Q0 will result in complementing the Q1. So Q1, if assume it is 0 initially, it will stay 0 until this falling edge. And this falling edge, it will be complemented or toggle, and it will stay the same until we go back or receive the next falling edge. Of course, this is just one example on a counter. You can design counters in different ways. So basically, if I look at both Q0 and Q1, initially this was 0, this was 0. So what is the value here? It is 0, 0. And it will stay like this during this period of time. Here, Q0, 1 is 0, this is 1. So in this period, the value is 0, 1. And here, I'm sorry, here, yes. Here we have 1, 0. So this is 1, 0. and here we have 1, 1. So the value here in the counter 1, 1, and then it goes back to 0, 0. So basically, this circuit is counting 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, and so on. As long as this input is ticking, then the counter will keep counting in this order. Now, if this input is as I draw it here, which is basically a periodic square wave with certain frequency or t, or certain period, okay, then I can say that every increment is basically one time unit, which is t. So this is t, and so on. Now, this instant when the counter changes from 1, 1 to 0, 0 is very important instant, which is basically the overflow instant. This is a 2-bit counter. It can count from 0, 1, 2, 3. When it reaches a 3, 3 is the maximum, so the counter rolls back. It rolls over back to 0, 0, because the maximum value that we can store is 1, 1. So here we have an overflow, which is basically an important event that is used by all timers in order to notify, let's say, the CPU that certain period of time has elapsed. So basically, the time that is measured by this counter is basically the number of increments times t, where t is the frequency or the period of the incoming trigger or the incoming clock. So if the number of increments is 1, then this implies that only one period has elapsed. So we have counted this. If the number of increments is 1, 0, then the time that has elapsed is this. If it is a 3, then it is this time, and so on. Okay, so what is the maximum time that can be measured by any counter? Basically, it is 2 to the power n times t. 2 to the power n times t. What is 2 to the power? What is n? N is the number of bits in this counter. This is the maximum time. This is the time, the instantaneous time. This is the time at any instant of time. So this is the maximum time that can be measured before overflowing the timer, which is the instant when the maximum value changes to the minimum value, So this is basically how do we construct the timer. We need a counter, and we drive the counter by a periodic square wave with known frequency. So now we can measure time. We can measure time based on the incoming clock. So basically we are counting how many edges or how many periods have elapsed. So technically we can measure time. And this is what we have in our watches usually. We have a time base, which is the second, which is our time resolution. We cannot measure something less than a second, let's say in our mechanical watch. So it is 1 second, 2 seconds, 3 seconds. And we use this whenever the seconds counter reaches 60, we increment the minute counter. When the minute counter reaches 60, we increment the hours counter, and so on. So this is basically the structure of counters. This is one way to construct a timer. Now, what if this input, or basically, let me ask this question. What does this counter count? What is this counter counting actually? It is, as I said, it is either counting, I can think of it as it is either counting these edges, 0, 1, 2, 3, or it is counting the number of periods, So now, what if this input is not actually periodic? What if this input is not periodic? Will that make a difference? Actually, no. But the circuit that we are seeing in front of us will not be a timer, because its trigger is not a periodic square wave with known time or with known period. In that case, the circuit that we have in front of us will be called counter, because it is just counting. So we may have something like this for the input. So the input is not periodic square wave. So what will be Q0 and Q1? Basically Q0 will complement on every falling edge in our circuit. So it will be something like this, then it will be something like this. Now Q1, initially let's say it's 0, so it will stay 0 until there is a rising edge or a falling edge on Q1. This is the trigger for Q1. So what is the count? So in here we have 0, 0. Here we have, throughout this period, we have 1, 0. We have 1, 0. Then here we have 0, 1. Right? So what are we counting here? Still, we are counting edges. Right? We are counting edges. However, these edges are not equally spaced in time, right? So we are just counting edges. So if our counter is triggered by an input that is not periodic, then it is called basically a counter circuit. It is just a counter. It counts something. It counts events, and these events are these edges, falling edges or rising edges. It depends on how the timer is designed. However, when the input is periodic square wave, our counter circuit, it is the same circuit, is now counting time edges, so it can be used to measure time. It can be used to generate time. That's why if you go to most microcontrollers, the counter or the timer system or the timer module is usually called timer/counter, because you can operate this circuit, which we have on the slide, as a timer to measure time, or as basically a counter to measure asynchronous events or aperiodic events like this. For example, this could be the signal that is coming from a switch that is connected to the microcontroller, and basically you want to count how many times the user pressed the switch. Just you want to count how many times the switch is pressed. Now, this is usually seen, as I said, in most microcontrollers that allow you to change the input. For some microcontrollers, the clock input to the counter is fixed. It is always connected to the oscillator. So it is basically just a timer module. However, in other microcontrollers, this input, which is the trigger for the counter, is configurable. You can connect it to the oscillator, or you can connect it to some external input so that you can count events, asynchronous or aperiodic events. So sometimes they call it a timer, sometimes they call it a timer, counter. It depends how you clock this hardware, whether using a periodic square wave or an aperiodic signal. All right. So this is just the basic idea of how do they build the timer system. This is the core of the timer system in any microcontroller, which is basically a counter that counts the periods or counts the edges, which implicitly implies counting periods and time. All right, so that's very quick overview on what is meant by timer or counter. And as I said, the core is the counter circuit, and one that counts events. And these events could be periodic if the input clock is periodic, or could be aperiodic if the input is basically some input that's coming from some other system, such as a switch or a sensor or whatever. Any question? All right, so let's now see how this is implemented in the HCS microcontrollers, and what are the features that are the timing features or the timing functions that are provided and available in this timer module. Now, the HCS microcontrollers, they have a standard module, timing module called the TIM module, which basically has 16-bit timer / counter. So there is a slash missing here. It is a timer / counter. What does this imply? As I just said, it implies that this counter can be either triggered or clocked by a periodic square wave or by some aperiodic square wave. Now, the size of this timer is 16 bits, or this counter is 16 bits. This implies that the maximum count value is 2 to the power 16 minus 1. This is the maximum value that we can store in this counter because it is 16-bit. So this is the maximum value. Okay, and so how many times we can increment the counter before it go back to 0? In other words, before it overflows, 2 to the power 16 increments, right? If you want to count from 0 all the way to 2 to the power 16 minus 1 and then back to 0, then you have to increment the counter 2 to the power 16 increments. So this implies that overflow occurs after 2 to the power 16 increments. So the maximum number of counts that you can count before overflow is 2 to the power 16. The maximum value in binary to be stored is 2 to the power 16 minus 1. And if I am using this counter as a timer, then the maximum time that I can measure is basically 2 to the power 16 times t. And what is t? As we will see later, this counter is clocked or triggered by the E clock. So it is times E clock, 1 over E clock, times prescaler. So similar to the case which we saw in the A to D converter, which we saw in the real-time interrupt, which we saw in the SCI modules, we can always scale the clock. So basically the period, this is the frequency. So this is the period of the timer, which is basically the E clock scaled by some value. This scale value could be 1. We can make it 2 or 3 or 4, as we will see later, in order to increase the period of time that we are measuring, or in other words, to increase T, which is the period of the clock that is driving the timer. What is the effect of this? The maximum time that we are measuring will increase. If we increase the prescaler, the maximum time will be larger, of course. Okay. So this 16-bit counter can be clocked by the E clock, and in this case we can measure time. It can be also operated as an accumulator, or basically counter to count some aperiodic event or asynchronous events. And as I said, we can count up to the power 16. Now, this is the basic or the core of the module, which is a timer or a counter that can be operated as a counter or a timer. However, this core hardware can be used to to implement two important timing operations, which is the input capture and the output compare. The input capture and output compare. And what is meant by input capture, output compare? As we will see later, input capture implies to capture or to record the time of some event. So basically, this timing function is just like the stopwatch. In the stopwatch, you have the clock running, and when you see some event, you just hit the button and the time stops, right? So this is what happens in the input capture operation. You will have the counter in this module operating as a timer. So there is a time that is running, and you have a hardware that can be configured to monitor some external event on one of the pins of the microcontroller. And once this event occurs, you can record or read the time, the current time of the timer. So that's why it's called the capture. When the event occurs, and this is an external event that is monitored at one of the pins of the microcontroller, you basically record the time and store it in some place. For the output compare, basically you need to have the counter running as a timer or working as a timer. And whenever the timer reaches some value, some time, some predefined time, you want something to be triggered. You want something to happen at one of the pins in the microcontroller. So basically, that's why it is called output compare. You continuously compare the current time with some set value. And when they are equal, you trigger something. You force something to happen on one of the pins associated with the microcontroller, as we will see later in the details when we discuss both operations. So these two operations are supported and implemented by the TIM module using this counter or timer and some additional hardware to monitor the input events or to perform some operation to force some output value when the compare is true. Okay, now this basic timing module is extended in some models in the SCS12 microcontrollers, and specifically those microcontrollers targeting the automotive industry. So the same the same functionalities that are in the TIM module are available in the enhanced timing module, the ACT module, in addition to some other features that we most likely we will not discuss. We need to capture or to grasp the basic idea of the timing system and the basic and the common functionalities that are associated with it. So most of our discussion will be about the things related to the TIM module. Okay, so now this timing module, which is the TIM, as we said, has a timer or counter and can implement input capture or output compare. So there should be some interface with the outside world, or in other words, pins, in order to monitor the events that we want to capture their times, or to output some value when there is a there is equality between the time, the current time, and the set value, and that is achieved through port T. Port T pins can be used as general input-output pins, or they can be used as the input-output input capture, output compare pins. For example, you can configure this timer module such that whenever a falling edge appears on pin number 0 from port T, which is IOC 0 pin, the input-output channel, input-output channel 0, which is pin 0 from port T, whenever there is a falling edge on this pin, you can configure the module, the TIM module, to read the current time and store it in some special register. This has many applications, as we will see later. For example, you can configure input-output channel number 7, input-output channel number 7, which is technically pin number 7 from port T, such that when there is a match between the current time and the set value, you force this pin to be high, or you make this pin low. You output 1 or you output 0. And again, this also has many applications. So these pins, or port T, basically is multiplexed or shares its functionality with the TIM module whenever we enable the input capture or the output compare functionalities on any of these pins. And we will discuss the details how to use the input capture and output capture compare in this part later. Okay, so this is the general block diagram of the TIM module. At the heart and at the center of this module basically is the 16-bit counter that we just talked about. That can be used as for timing operations. The input to this block, of course, is a clock that can be used to trigger or to clock the timer register. In addition, there is a 16-bit pulse accumulator A, which is used as a counter, which can be used to count the event. So the clock is basically connected to the 16-bit counter, and there is additional counter actually. It is not the same counter. Additional counter called accumulator A. It is different than accumulator A that is inside the CPU. This is pulse accumulator A, which can be used to count event. So I just, I said it, I need to correct it. This counter is basically a timer. It cannot be used as a counter. It is only connected to the clock, which is the E clock. There is another counter, which is the pulse accumulator counter, which is also 16-bit, which can be used to record events. We will see how is this done. And the events are basically either rising edge or falling edge on some pen. Now, on the right here, we have the input-output channels, which are basically the pins from port T. So this is pin 0. This is pin 0 from port T. This is pin 1, and so on. So the port is multiplexed. And this pin, as we said, basically can be used if we configure this pin for input capture, then it will be configured as input, and whatever happens here on this pin, such as a falling edge, rising edge, low level, high level, can be configured to capture the value in the timer and store it in a special register. So there is a hardware here that can be configured to capture what is going on here. When something happens, according to the configuration, the timer value is captured and stored in some register. The same thing for the output compare. This pin can be used to output 1 or 0 whenever the timer value reaches some predefined value or some set value. Then we can force the pin to be high or to be low. Okay, so there are 8 channels that works in the same. They are independent channels and they operate in the same manner. In order to do all, to control and use and configure this module, basically there are special there is a set of special registers as usual. For every module, there are registers that can be used to use the module and configure its settings and features. Now, this module is associated with a large number of interrupt sources. The first interrupt source is the timer overflow interrupt. So whenever this 16-bit timer overflows, in other words, it goes from the maximum value to the minimum to 0, then this event can be used to interrupt the CPU. It can be used to interrupt the CPU. The same thing for the input capture functionalities. Every channel has its own interrupt, so that whenever the condition that is the channel configured for occurs, this event can be configured to interrupt the CPU. For example, if input capture, if IOC 0 is configured as input capture, in other words, it is only configured to capture some event, then whenever this event happens and the time is captured from the 16-bit counter to the registers, this event can be used to interrupt the CPU. Similarly, let's say if IOC3 is configured as an output compare channel. In other words, whenever the timer value reaches some set value or predefined value, something happens on this pin, then this event can be configured to interrupt the CPU. So we have 8 interrupts, one for each of the IOC channels, IO channels. The last two sources of interrupts are related to the accumulators, to the pulse accumulator, and we will talk them when we discuss the pulse accumulator in the second part. All right, so this is a brief overview about this timing module. In the coming few slides, we will discuss the timer operation alone. Then we will discuss the input capture operation and the output capture operation, how to configure each of these operations and some applications on using these features. Yes, Yazan.
دكتور كنت بدي أسأل شو علاقة ال 16 bit counter بالاوتبوت compare؟
ما لهم علاقة، بس هو هذا الكاونتر ال 16 bit pulse accumulator موجود داخل هاي الموديول.
اوكي، طب يعني هلا
يعني هدول الانبوت اوتبوت كابتشر channels, their operation is associated with this counter, which is basically connected to this clock, because these are purely timing features, timing operations. So you need time, and to have time, you need your counter to be connected to some predefined clock. While this counter below can be connected to any event. So basically, it counts events. It's not connected to the e-clock. Counter. The counter, we will see what is the input to this counter. Where the input of this counter comes from. Okay. Okay. So now let's, how many minutes do we have? We have 10 minutes. Yeah, we can go over this very quickly. So let's now discuss using this system, this timer system, as a timer, basically as a timer or a free running timer. It is just a counter that is connected to the clock, and it is counting periods, and when it reaches the maximum, it overflows. So it is just an indication of some elapsed time. So basically this feature can be used to measure time or to generate delay. For example, you can enable the timer to start counting using some, based on some frequency for the scaled version of the e-clock. So basically there will be a maximum time. Once that maximum time is reached, when the timer overflows, then you can tell the CPU that 1 second has elapsed or one millisecond has elapsed through interrupt or through pulling. You can pull the flag, the interrupt flag of the timer overflow. So basically this free running timer is the 16-bit counter that we saw in the block diagram. The counter value is stored in a special register called the TCMT register, the timer count register, which is basically the same counter. So this counter is a register that is addressable or accessible by the CPU, and it has an address and a name. So its name is the timer count register. So the count value is stored in this register. And as I said, this register or counter is stored or triggered by the e-clock with a prescale. And the purpose of the prescale is to increase the period of the e-clock or the timer clock, in other words, so that we can measure longer time. Because if we increase the period, we can increase the overall time, right? We can increase the maximum time. So here is an example which can be easily understood if we have the formula. If you go back to the formula, let me go back. This is the formula. So now, if the bus clock is 1 megahertz, or sorry, if the bus clock is 1 megahertz, in other words, the e-clock, bus clock implies the e-clock with a prescale with 1, then the timer increments every 1 microsecond. Because if you remember, we say this is the maximum time. However, the time at the instantaneous time is basically the number of increments or the count value basically multiplied by t. So now t is the maximum t. The e-clock is 1 over 1 times 10 to the power 16. I'm sorry. The e is 1 times 1, 10 to the power 6, multiplied by the prescale, which is 1, and the count value. So every increment is basically 1 microsecond, right? Whenever we increment by 1, then this is equivalent to 1 microsecond. Now the maximum time that can be measured in this timer is 2 to the power 16 microseconds, given that the prescaler is what? Is 1. Because if the prescaler is 1, then the maximum value is 2 to the power 16 times 1 microsecond times 1 microsecond. We can increase this time by simply making this prescaler larger than 1. If we make it 2, then the maximum time will be 130 milliseconds. 3 will be, and so on. Okay, will be 195 milliseconds and so on. So this timer is basically the time base of the free running timer, and as I said, it is the time base for the input capture and the output compare function. Okay, now in order to enable this timer to start counting, in order to specify the prescaler, what is the value of the prescaler, in order to determine whether the overflow interrupt event of this timer is enabled or not enabled, we need to use special registers that are related to this timer module, which are the control register, timer system control register 1, timer system control register 2, and the timer flag register number 2, timer flag register number 2, which is the same case that we had earlier with the A to D, the real-time interrupt, the SCI. Whenever we want to work with some peripheral device inside the microcontroller, we need to work with some special function registers. Okay, so let's go through very quickly. They are straightforward, these registers, and the idea, I think, is clear to you. The first register is the control register number 1. We have 4 bits in this register. The most important one is this bit, which is the timer enable bit. So by default, this timer is not ticking, is not incrementing on reset by default. So by default, it is disabled, because 0 implies the timer is disabled. In order to save power, if you don't want to use the timer, why to turn it on, or why to enable it? 1 allows the timer to function normally. Now the other 2 bits basically specify what happens to the timer when the CPU or the microcontroller enters the waiting mode or the freeze mode. So this is also, we are familiar with it, whether we want the timer to continue counting when we enter the wait mode, or we want to disable the timer when the microcontroller is in wait mode. The fourth bit, which is the fast clear flag, which is basically similar to what we discussed with the A to D. We said there is a fast way to clear the flags. So this is the timer fast flag clear. So when we talk about the flags, we will come to this later, but basically in order to clear the flag, the timer flags, so the timer interrupt flags, and we saw we have what? 11 flags associated with this timer. Basically, you need to write 1 to the flag. You need to store 1 to the flag. However, if you set this flag, you can clear the flags by simply, depending on the mode of operation, by simply reading another register, some register. We will come to this later, but the details are here. You can read them. But this is just basically to enable the fast fast flag clear mode operation. The control register number 2 basically has the bits that you need in order to specify the prescaler or the scale value for the E clock. And basically we have a scaler up to 128 in steps that are power of 2. 2, 4, 8, 16, 32, and so on. So by default, the prescaler is 0 when you enable the timer. The other bit is the timer output in the timer interrupt overflow interrupt enable bit. So basically, this is one of the interrupt enable bits that we have for the 11 interrupt sources. So whenever the timer overflows, you can, as we said, interrupt the microcontroller to do something. And this basically notifies the microcontroller that certain time has elapsed. Now for this note, this is related to the third or bit number 3. We'll come to it when we talk about the input-output, the input capture and output compare functionalities. The timer flag register has only 1 bit. Number 2, flag register number 2 has only 1 bit, which is bit number 7, which is the timer overflow interrupt flag. So this flag is basically set whenever the timer count register overflows. In other words, when the timer overflows, this flag is set. So we can either pull this flag to know whether some time has elapsed or not, or we can enable the interrupt service associated with this event. So next time we will go through an example to use this free running timer in order to perform certain operation related to time. Okay, then we will go through the input capture and the output compare functionalities. All right, any question?
دكتور بس عندي سؤال واحد. يعني in general وين هاي الاشياء بتكون مخزنه يعني اللي بتخلي المايكرو كنترولر مثلا فور اكزامبل انه اذا بحط البيتس تبعون البري سكيل مثلا 3 زيروز معناته بري سكيل 1 يعني اتسترا، هاي الاشياء وين بتكون مخزنه بالضبط؟
هلا هدول كلهم زي ما حكينا هم عباره عن سبيشال فانكشن ريجسترز. يعني داخل الموديول نفسها في مجموعه من الريجسترز اللي بخزن فيها هاي الفاليوز، تمام؟ والسي بي يو في لها اكسس على هدول الريجسترز. يعني انا عم برسم على اللوح يس انيبل يعني مثلا هاي السي بي يو اللي داخل المايكرو كنترولر، فرضا هذه التايمر موديول، او هاي اي بريفرال ديفايس موجود هون. هلا هون في ريجسترز، هدول الريجسترز are accessible by the CPU, and the CPU can read and write to these registers. Now the values of these registers are taken and used by some hardware inside the module in order to perform the required operations. فهمت
أوكي.
ولا مش كثير؟
يس، فهمت الصورة العامة، بس يعني مثلا شو اللي بيخلي فور اكزامبل انه انستراكشن معين انه السي بي يو تفهمه على انه تسوي هيك؟
كيف يعني؟
يعني مثلا انا لما اكتب برانش سمثينج، كيف السي بي يو وين السي بي يو كيف تعرف
يعني
انه
مثلا انت بدك تشيك هل التايمر سوى اوفر فلو ولا لا مثلا، تمام؟ فشو بتحكي؟ برانش كلير، شو بنحكي احنا؟ تي اف ال جي 2 بعدين كوما تي او اف او بت نمبر 7 تي او اف ستار. هاي الستيتمنت شو معناها؟ طالما البت رقم 7 اللي هو التايمر اوفر فلو انتربت فلاج ما صار واحد، وين هذا موجود الفلاج؟ بالريجستر هذا ما صار واحد، السي بي يو راح تضلها عند هاي الانستركشن. طب هاي الانستركشن لما تتنفذ شو اللي راح يصير فعليا يا يزن؟ فعليا السي بي يو تحكي بدي هذا البت، هذا البت وين موجود؟ هذا البت موجود بهذا الريجستر. طب هذا الريجستر وينه؟ موجود هون، هيو تي اف ال جي 2 مثلا. فراح تروح تسوي اكسس عليه وتقرا قيمه الريجستر، وتحديدا تقرا قيمه البت هذا.
يس اكزاكت.
عشان هيك سميناهم هدول، اذا تتذكر يمكن حكيتها انا او ما حكيتها ما اعرف، هدول الريجسترز او الديفايسز والبورتس سميناهم ميموري مابد اي اوز، ميموري مابد ديفايسز. كيف يعني؟ انه السي بي يو بتتعامل معهم كانهم ميموري، بس هل فعليا هدول الريجسترز موجودين داخل الميموري؟ لا، هم لهم ادرس زي كانهم ميموري لوكيشن، بس هم فعليا لا، هم فعليا ريجسترز فيزيكلي موجودين داخل الهاردوير موديول اللي عم بتعامل معها.
يس.
فالسي بي يو بتتعامل معهم عادي، زي كانه ميموري لوكيشن. يعني بدال ما تروح على هاي الميموري، بدال ما تروح على الميموري بتروح على الديفايس اللي هون.
يا تمام.
لانه هذا كومن بس هلا، فاما بتروح هون حسب ايش؟ حسب الادرس. يعني الادرس هو اللي بحدد، الادرس بس هو اللي بحدد الفاليو الموجوده على الادرس بس، هي اللي بتحدد هل انا عم بحكي مع هدول او عم بحكي مع هدول.
ايوه يس.
تمام؟ يعني السي بي يو بتبعت هذا الادرس اوت، وبناء على هذا الادرس بصير انيبل اما للميموري او بصير انيبل لهذا الريجستر او لهذا الريجستر او لهذا الريجستر اند سو اون.
اوكي. طب هلا دكتور مثلا فور اكزامبل خلينا نحكي نعمل اديشن. اوكي، كيف السي بي يو بتفهم ذس انستراكشن؟ يعني هي لما تيجي تقراه انه